Hello everyone, welcome to Dakshana E classroom program. So up to last lecture we discussed about inductance, we talked about self-inductance, we talked about mutual inductance. Self-inductance when current is flowing in same coil and that will result in some magnetic flux linked to same coil, and whenever some current is changing means or maybe some other means the flux linked to the coil is changing, then this coil will try to oppose that, and this opposing property we measure in terms of inductance. Similarly, we saw actually that when we have, let's say, two coils, is it? So when we are having, let's say, two coil, this is coil 1 and another coil is, let's say, this is 2. So I will say this is 1 and this is 2 coil, is it? And we can write it in this way. So this is coil 1 and another coil is, let's say, this. So 1 and this is outside is coil 2. So now what is happening here, when current is flowing in this coil 1, we normally call, like, primarily flux is linked to coil 1. So we call like when current is flowing in coil 1 means primarily we are considering here flux in coil 2 due to current in coil 1, is it? Then coil 1 will be considered as primary coil. So when current is flowing in coil 1, it is primary coil, and flux is linked to coil 2 due to current in coil 1, it is called secondary coil. So primary and secondary means this, like if I am saying current is flowing in coil 2 and I am considering the flux due to current in coil 2, flux through coil 1 due to current in coil 2, then this will be my primary coil, that will be my secondary coil, is it? So this is, and we have seen, like, when two coils are there, then the mutual inductance we just calculated, that's coming out to a mu naught into N1 N2 A into L, where A is this area. Basically you can write, if I am writing this is A1, so it will be A1 area. Clear? And we calculated this in just last part. We got that mutual inductance depends on the medium between the coils, depends on the number of turns on coil 1, coil 2, and area of coil 1 and length of the for what length they are basically coupled. So that depends mutual inductance. Similarly, if I write, if let's say L1 and L2 are self-inductance of coil 1 and coil 2 respectively, and M is their mutual inductance, then we have some relation between M1, M, L1, L2, and that relation is this: M is equal to K under root L1 into L2, where this K is called coupling factor, COUPLING, or factor of coupling, is it? That actually depends that how two coils are placed. See, in this situation, so here K is defined as basically flux in secondary coil divided by flux in primary coil. This is termed as K, that is coupling factor. So in this situation here, like if coils are like this, let's say current is flowing in this coil, primary I, and this is my primary coil, and another coil secondary is also linked like this. So this is You can see secondary coil may not be visible clearly. I'm just trying to. So here you can see it's like completely coupled. In this situation, flux linked in coil 1 will be exactly equal to flux linked in coil 2. So in this situation, your K will be exactly 1. Clear? So this for this situation I can write the coupling factor will be equal to 1 when flux linked in both the coils is equal, right? And similar manner, if there is some situation like this, so in this situation current is flowing, and here, so let's say this current is flowing, this is primary and this is secondary coil. Definitely you can see magnetic field lines will be there, and this here complete flux is definitely not linked into this coil. So here I can write K will be definitely less than 1 because some amount of flux will be linked, so it will be also greater than 0. And if I am placing like coils like this way, this is one coil, current flowing primary, another coil placed this way. So you can see here there will be no flux linked in secondary coil. In this case you can write K will be equal to 0. So K actually depends that how two coils are placed, and we call that coupling factor, and based on coupling factor mutual inductance also depends, because like if there is no flux linked to coil 2 due to current in coil 1, then definitely there is no mutual inductance, right? So this is a little bit about mutual inductance. We saw a few things in the last part about mutual inductance. Let me like solve some problem based on it. Okay, consider next problem here. So we have the problem, consider two concentric coplanar circular loops A and B of radii r, small r and capital R. This is B, this is A. Respectively, current I flow in loop A. Find the magnetic flux through loop B. So due to current in loop A, you are asked to find the magnetic flux through this bigger loop B, and also find the mutual inductance. So this is our problem, and this condition is also given, don't forget that. So now see here actually what is happening. If I'm just going simply straightforward, then in this situation the magnetic field due to this current in coil A, because this is small r is very smaller than capital R, so due to this at every point the magnetic field will be non-uniform, and then calculation of magnetic flux due to current in coil 1 through coil 2 will be like difficult. It will be like very lengthy and very difficult part, but we can make it easy by considering, by going with the help of mutual inductance or some like basically different than this way. So here first thing is, it's not easy to calculate flux through coil B due to current in coil A. But we can go here, let's consider current I flow in coil B, right? Then if current I is flowing in coil B, then by this I can write flux through coil A, is it? So flux through coil A can be calculated easily, right, due to current in coil B. So that I can write first magnetic field at center of coil B due to current in coil B. This can be calculated. This is mu naught into I divided by 2R. Clear? So what we are doing here, if I am considering the in question, it's given in coil A there is some current I flowing. Due to this current, it is asking magnetic flux through coil B, and the point is it's not easy, it's very difficult. There will be variation and integration will be also not easy. So what I'm going is that let's consider there is some current I flowing in coil B. So I am calculating magnetic field due to this current in this coil at this center. Because this condition is assumed, then I can say almost at center the magnetic field is uniform. Understanding? Then I can get easily magnetic flux through coil A. So I got the field at center, means field in the loop A is given by almost equal to this. So flux through coil A due to current in coil B. So I can write flux through due to current in coil B. This is equal to what? That is given by mu naught into I divided by 2R multiplied by pi R square. Getting it? Pi into small r square. So this is the flux, and this flux can be written as phi AB is equal to what? Mutual inductance into I. So this implies mu naught into I into pi R square divided by 2R, and this implies mutual inductance is equal to mu naught into pi R square divided by 2 times capital R. So I got mutual inductance, right? Now with the mutual inductance I can easily write, if current in coil A is I, then flux linked to coil 2 or coil B due to current in coil A is given by M into this I. So now flux through coil B due to current in coil A, this is given by M times I, and this comes out to be mu naught into pi R square divided by 2R multiplied by I, and this is answer. So here you can see how easily we can get it. So I hope this part is clear. What the complexity is that if you're going straight forward, then you will get stuck. It will be difficult problem. It's given current in this coil, asking flux through bigger loop. And if you are going straight forward, finding magnetic field due to this current at different point, it will be very complex process, difficult to calculate. So what we have done is we have considered a current in this bigger coil, we calculated flux through this smaller coil, we got flux, we got magnetic field, flux, and we got mutual inductance. And with the help of mutual inductance, I can write if current in coil A is I, then flux linked to coil B due to current in coil A is given by simply M into I, and this is your straightforward answer, and mutual inductance is this. So this is one application of mutual inductance. Okay, so the next is dot convention of coupling. What it is and why we require it, let me tell you first this. So here the point is that if I am, let's say, writing a coil, inductor coil this way, is it because we conventionally denote a coupling or like a coil this way. In this situation, when current is entering here and actually exiting through this way, still we don't know that how exactly this coil is placed, what is exactly its orientation. Means if you look at it from this side, then exactly it's going this way or it's going this way, we can't clear. Like that point is not clear, that part is not clear. So even if we apply the right hand thumb rule for this coil, still we can't say clearly that whether this is north pole or this is south pole. Understanding? And if that is the situation, then it creates problem to us when we want to see the flux of another coil. Let's just consider this way. Okay, so I don't know whether this coil has magnetic field lines this way or like opposite way. I'm like whether this way or opposite way. So if I'm taking this way, and let's say magnetic field lines of this coil is also exactly in same manner, then I will write magnetic flux net through this coil 2. Phi 2 will be like this is phi 1. I'm like flux through coil. So 1 I can write L2 into I2, current in coil 2. Is it? Through 2. And this flux, if both are in same direction, then it will be added M into I1. But from this symbol we can't say with surety whether they will be added or subtracted. So to remove that convention, to remove this confusion, we have just followed one convention, that conventionally we will write this, that, and according to that this problem gets solved. So what is that convention? Convention simply says that whenever we are having one coil, whichever the and dot is placed, that is considered as the north pole of magnetic field. So dot basically is pointing towards north pole of magnetic field. So in this situation, it will like this problem will be simply resolved. See it how. Okay. So now if I am saying let's say dot, here I am like marking it with different ink. So in this situation, let's say dot is here, and here in this situation, let's say dot is here. So now you can see actually here the magnetic field lines of this will be in this manner. They will be this way, means direction north is this way. Is it magnetic field lines? And magnetic field line due to the current in coil 2, because here north pole dot is here, so magnetic field lines due to current in this coil will be pointing this way. Is it clear? Now you can see it's definitely clear that they are in opposite direction. So if I am writing this is current I1 and current in coil 2, I am taking this is current I1 and this is current I2, and this is coil 1 and this is coil 2. So the net flux through coil 1 or through coil 2, I can write it very easily. See it how. So the net flux through here phi 1 means through coil 1, so it will be equal to what? Phi 1, it will be equal to L1 into I1. This is the flux through coil 1 due to current in itself. And here you can see this flux is this way and it flux this is opposite, so I will write it's minus M into I2. This is the flux linked to coil 1 due to current in coil 2, and exactly in same manner I can write phi 2 will be equal to L2 I2, and exactly net flux through this will be L2 I2, and due to this it will be opposite direction, so I will write it minus M I1. We can write it easily. And similarly, if I write here, let's say this is north pole and here this is the north pole, so means magnetic field lines will be parallel. You can write both will be pointing in same direction this way, and here also they will be pointing in same direction. So now in this situation you can see the magnetic field lines net due to this they are flowing this way, pointing in this direction, and these will be also added, so net flux through this coil will increase. So now I can write net flux through coil 1, so it's phi 1, that this is current I1, its self-inductance, coil 2, coil 1, mutual inductance M, current I1, current I2 and I2, so on. Right, so this is the situation. In this situation I can write, you can imagine easily, net flux will be added, so flux through this is L1 I1, this is a flux linked to coil 1 due to current in coil 1, and you can see here, so this flux this way and these magnetic field lines also same parallelly, so it will be added, so it's M into I2, and exactly in same manner I can write net flux through coil 2 can be also written as this is L2 I2 plus M I1. So this dot convention simply remove our that confusion whether both flux should be added or subtracted. That is clear once we have this dot marked on the coil. Okay, so let's next see the combination of inductor means series combination, parallel combination. Just like resistor and capacitors, we have series parallel combination and equivalent capacitance and resistance. Exactly in same manner here also we have series parallel combination, and let's see what is that exactly for inductors. Okay, so let's see, next is combination of inductors, and that is series combination with mutual inductance. I will write the result also when mutual inductance is taken as 0 or there is no coupling, no flux is linked, means that. So in this situation I am considering the case when mutual inductance is also there, so automatically it's given to us that mutual inductance for this coupling is given as M, and we have here two coils connected in series, L1 inductance, L2 self inductance, and this way. So we want to replace this complete system with some single coil, and what should be its equivalent inductance. So for that I can write here current flowing I, and here also it will be I. North pole pointed this way, so I can here write flux, net flux here through coil 1 can be written as what? So you must be clear now here, north pole here, so they are pointing in same direction, means the flux will be added here. So this is equal to L1 into I plus M into I. Similarly I can write phi 2 is equal to L2 into I plus M into I, and this I can write EMF E1 is equal to minus d phi by dt, or if I'm just writing magnitude, then I can write it, this is L1 di by dt plus M di by dt, or I can write L1 plus M into di by dt, and so on. Exactly in same manner E2 can be written as d phi 2 by dt, and this is equal to L2 di by dt plus M di by dt. Is it clear? And for this system, what I can write here, VA minus VB is equal to minus L equivalent into di by dt. Clear? Now here if I apply KVL in part AB, then I can start from A, so it's VA, right, I'm going in the direction of currents, so it's minus L1 di by dt M di by dt, this minus L2 di by dt plus M di by dt, this, and is equal to B. Is it clear? I need to check, so here I can write VA, then it will be minus of L, so it will come actually here now plus. So that is the condition, and VA minus VB, I'm going VA minus L di by, that's correct. So this is the situation, and it will be VB. So now I can write this implies VA minus VB is equal to L1 plus L2 plus, if I just add both of them, that is 2M whole multiplied by di by dt, and here we are getting simply this is L equivalent into di by dt. So this is VA minus VB. Let me write equation 2 and this equation 1. So comparing, because these two things should be equal, so I can write here comparing equation 1 and 2. I can write here VA minus VB should be L1 plus L2 plus 2M multiplied by di by dt should be equal to L equivalent into di by dt. Di by dt is simply just getting cancelled out, and we are getting here L equivalent is equal to, this is L1 plus L2 plus 2M. Right, so here we can get, this is the L equivalent connected in series, L1 plus L2 plus 2M. Here this 2M will be plus or minus, that will depend exactly on dot convention. This is not universal result that always in series combination your L equivalent will be L1 plus L2 plus 2M. Here we can write, actually if we have two inductor coil, let's say this and this way, and dot convention here and here same exactly manner. L2, this is mutual inductance, let's say M, and in this situation L equivalent will be L1, because you can write here it will be L1 minus M, L2 minus M, so it will be like your L1 plus L2 minus 2M will be L equivalent. Is it? So that is basically the condition for L equivalent in case of series combination. So I hope it's clear with you. So in this situation, sometime like in problem it's given, or the point is if mutual inductance is not mentioned, you need to check the language properly actually. So my point here is simply that if mutual induction is not considered, is it? So if mutual inductance is not to be considered, then L equivalent will be simply L1 plus L2 in case of series combination. So you can write it just like almost same, it's the addition equivalent is calculated in exactly same manner as resistance. Capacitor, it's opposite, like different or opposite of resistance, the way resistance is calculated, R equivalent. So here it's exactly same as resistance is calculated. Let's see similarly what is the L equivalent in case of parallel combination. So okay, so next is parallel combination, and here we are considering the case without mutual inductance. So there in parallel combination there is no coupling, no flux is linked from coil 1 to coil 2. So let's consider this is the situation. We can easily identify this is parallel combination. That is how things are connected. Self inductance L1, L2, current I1, I2 and total current I is coming. We want to replace this system with this which is having same potential difference, same current is flowing, and we should have something L equivalent, and what is that? We need to find that. Okay, so here I can easily write in this situation VA minus VB is equal to what? It's L1 into di1 by dt. And I can also write VA minus VB is also equal to L2 into di2 by dt. Clear? Because in parallel combination potential difference remains same. Similarly for this circuit I can write VA minus VB should be equal to L equivalent into net di by dt. And this I can write by simple Kirchhoff's current law KCL. I can write this I is equal to what? I1 plus I2, and differentiating with respect to time, what I get here, di by dt is equal to di1 by dt plus di2 by dt. Now if I substitute from here, di1 by dt is delta V by L1, di2 by dt is delta, and so on. So substituting the values, this implies di by dt is how much? Delta V, means VA minus VB by L equivalent, and di1 by dt is VA minus VB divided by L1. I hope you are getting it. Simple. We know this straightforward. If L1 is the inductance, I1 is the current flowing, then potential difference between these points or these points will be same, so that potential difference can be related this way, exactly in same manner for second inductor. And KCL I can write this situation, net current at this I is equal to I1 plus I2. Differentiating I am getting this relation. From here I can write di1 by dt is delta V divided by L1 and so on. So I am substituting these values here, and here plus VA minus VB divided by L2. VA minus VB simply getting cancelled out, and here I am getting 1 by L equivalent is 1 by L1 plus 1 by L2, and this is the L equivalent in case of parallel combination. Sometime we need to find the current, how the total current I is dividing between inductor 1 and 2. So we need to have relation for I1 and I2 that we can get actually. So here this VA minus VB, this quantity should be also equal to this quantity. So I can write VA minus VB is equal to L1 into dI1 by dt is equal to L equivalent into di by dt. Is it? And from here dt cancel. If I just integrate both sides, then I will getting L1 into I1 is equal to L equivalent into I, and this implies just simply substituting I1 is equal to L equal to L1 L2 divided by L1 plus L2 and L1 into net I, and this implies I1 is equal to L2 divided by L1 plus L2 multiplied by total I. In same manner, I can write I2 is equal to L1 divided by L1 plus L2 multiplied by total current. So this way, remember these relations, these are also important, will be used in solving problems. So this is your parallel combination of inductors. So I hope you are getting clear with series and parallel combination of inductors. Remember the formulas will be used a lot frequently. Remember this relation also. Let's see some application of this concept. Okay, see problem here based on series parallel combination of inductors. So this is basic problem. Two inductors when connected in parallel, then L equivalent. So in parallel we have seen L equivalent is equal to what? It's basically L1 L2 divided by L1 plus L2, or I can write this is equal to 2.4 Henry, and in series combination it's equal to L1 plus L2, and that is equal to 10 Henry. So if I can write L1 is equal to 10 minus L2, and I can substitute here that I can write 1 by L1 plus 1 by L2 is equal to 1 by 2.4, and this implies 1 by 10 minus L2 plus 1 by L2 is equal to 1 by 2.4. We can simplify, this is one like only equation in L2. We can simplify it, and we are getting simplify it and getting it L1, L2, 4 and 6 Henry. You just check the calculation. So this is simple straightforward problem. Solving, you will get one is coming out to be 4 Henry and another inductor will be 6 Henry. And let's see another case here. So for the circuit shown below, switch is closed at t is equal to 0. Initially there was no current. So this is the circuit, EMF, battery like E, one resistor connected and two inductors are connected here in parallel, and this is the switch. Initially there was no current in either of the inductor or in the complete circuit, and the switch is closed at t is equal to 0, and now you are asked to find the current through both the inductor as function of time. Okay, so this is also like not much difficult. Let's solve it. Let's see how we can solve it with the application of parallel combination of inductors. So first thing is that here switch is closed. I can replace these both inductors with one L equivalent. Then I'm getting, this is my circuit, and this right, this is your circuit. Switch closed at t is equal to 0, EMF, R and L equivalent. So for this circuit I can write I as function of time is E by R, 1 minus e raised to power minus RT by L equivalent, and L equivalent is what? L1 L2 divided by L1 plus L2. So we got the total current flowing through this resistor or passing to these inductors, that is given by this. I can substitute the values, then I will be getting exactly what is the total current, that is coming out to be E divided by R. It's 1 minus e raised to power minus RT divided by L equivalent, L1 L2 into L1 plus L2. So this is the total current flowing through both the inductors, or I will say through resistors. Now you can see simple, like here we are having, like, what is the situation we are having? This is the situation, two inductors like this, and total current I is passing here. It's I1, here it's I2, and this is L1 L2. So by the parallel combination I just derived actually that I1 is equal to what? It's L2 divided by L1 plus L2 multiplied by total I. If I just substitute this here, then I am getting I1 is equal to E L2 divided by L1 plus L2 multiplied by R into 1 minus e raised to power RT L1 plus L2 divided by L1 L2 whole. So this is the current through inductor 1. Exactly in same manner I can write I2 is equal to L1 divided by L1 plus L2 whole multiplied by I, and this is E L1 plus L2 multiplied by R into this is 1 minus e raised to power minus RT L1 plus L2 whole divided by L1 L2 is complete. So this is through inductor 2. So that you can see with the help of series parallel combination we can solve this problem also very easily, right? So let's see the next problem. Okay, consider next problem. So here we have in the following circuit, switch is closed at t is equal to 0. Initially there was no current in either of the part, and find the current and EMF through each inductor as function of time, also find power generated across resistor. So this is the problem. Let's see how we can approach it. So first thing is here we have three inductors. These two are connected in series and across this in parallel. And there is also mutual reductance, and the dot convention not 4 is also given to it. So if I just get this is in series combination, then L equivalent, let's say 1 right, this comes out to be what? It's like L1 plus L2 plus 2M. You can write it because they are, the flux is in same direction. Now this and this in parallel, then I can write L equivalent net, this is prime. This comes out to be L equivalent prime into L3 divided by L equivalent prime plus L. If I substitute the values, then I am getting this is L1, L2, 2M multiplied by L3 divided by L1 plus L2 plus 2M plus L. So this is L equivalent. Now I can replace this complete system, is it, with this battery, switch closed at t is equal to 0, resistor, and here this complete L equivalent. So now for this circuit, if it is closed at t is equal to 0, I can write now I function of time is given by E by R 1 minus e raised to power minus RT divided by L equivalent. So I got its E divided by R 1 minus e raised to power minus RT divided by L equivalent, which is this, and that is equal to L1 plus L2 plus L3 plus 2M divided by L1 plus L2 plus 2M multiplied by L3. So this is the net current across this resistor I can write, or through this complete system. So I got the total current, net current as function of time. Now if I talk about the power generated across, because this will be also the current across the resistor. So power generated across resistor, this can be written as power is equal to I square into R, and I can write I function of t whole square into R. I is this, so if I just multiply it, and this comes out to be power is equal to I square, so it's E square divided by R. This complete 1 minus e raised to power minus RT L1 plus L2 plus L3 plus 2M whole divided by L1 plus L2 plus 2M multiplied by L3. This is the power generated across the resistor, right? Okay. Next point, it is asking current through each inductor. So we got basically this L equivalent one, and here it's L3. So I got the total current here, that is I, function of time, this is given by this. Now this current is divided into parallel, like across this and this, and here in these two inductor current will be same. So now I can write here current, let's say I1, and here it will be, let's say I3. So now I can write current through inductor 1 and 2 will be same, and this I can write I1 equal to I2 is equal to what? It's this L3 divided by L1 plus L2 plus L3 plus 2m multiplied by I, and this I is this. So we got this is I1, I2. Similarly, I3 can be written as L1 plus L2 plus 2m whole divided by L1, L2, L3, 2m multiplied by again total current. So I got I1, I2, current through inductor 1, through inductor 2, through inductor 3. EMF, if like it is also asking, that will be dI1 by dt. I mean like EMF 1 L1 dI1 by dt, EMF 2 L2 dI2 by dt, EMF 3 L3 dI3 by dt. So now we have everything, I1, I2, I3. Just simply substitute it, you will get answer. So you can see like also here this seems a little bit complex, but if you are going proper step by step, you will get answer. It's not like much complex. You should learn the concept properly, what it is exactly. You should remember the formula without worrying much about like problem seems complex and like that. Just go step by step, you will be able to get the answer. So this is a little bit about series parallel combination and its application. Let's continue with the next topic. Okay, so the next topic is LC oscillator. Here L stand for inductor and C for capacitor. Inductor we have just seen here, and we saw something that inductor actually store energy. It doesn't dissipate if it is ideal inductor. And here when I am talking about LC oscillator, that means I am talking about ideal capacitor and ideal inductor. And in capacitor chapter you must have studied that capacitor is also storing or energy storing device. Capacitor store energy in the form of electric field and inductor store energy in magnetic field. So both capacitor and inductor are energy storing devices. So capacitor store energy in electric field and inductor store energy in magnetic field. This, like we have seen already, capacitor energy stored half CV square, inductor half L I square. So that is the thing. So now what is the case? So here let's say initially either we charged a capacitor, means a capacitor is connected to some potential V0 and some charge Q0 is given to it and having capacitance C, and it's connected to an inductor which is not having any energy. Now what happened actually in this situation, this is all observed thing, like that what we actually observe, that in this case, if this is the case, so like this capacitor act like a battery, understanding? So it starts supplying some current through this inductor, and here in the inductor, current will start growing. You know that if it is a battery, then current through the inductor will start increasing with time. The variation will not be exactly just the way when inductor is connected to an ideal battery. It will be like a little bit different, that we will derive that how exactly current here, current in the inductor will vary with time. We will get the expression. Okay, so the point is that here now energy initially is stored in the capacitor in electric field by storing charge. So when it is connected to inductor, this will act like a battery and it will supply some energy. And we will see that what happened exactly after some time, it completely discharged and total energy gets stored in the inductor. Now because inductor also can't dissipate that energy, this will also now start acting like a power source battery, and it will supply the energy to capacitor, and this process keep on repeating. For some moment of time, energy will be stored completely in capacitor. After some time, it will be stored completely in inductor, and in between it will keep on rotating. Understanding? So here we will see the energy keep on oscillating between electric field and magnetic field, and this system, this complete setup is termed as LC oscillator. Right? So here the charge and current varies like sinusoidal function. Let's get the expression. So I hope you just understood what is actually LC oscillator. So here we can initially give energy also to inductor. Maybe let's say inductor is connected to some circuit and it's having some energy stored in magnetic field, and now we are taking it out and we are connecting it to a battery like capacitor, which is completely uncharged, or initially like no charge is there on capacitor. In that situation also it will be exactly same way. It will be like keep on oscillating the energy. This system behave just like this case where we are having one spring block system. So this is spring block system. So here what happened actually, this is spring constant K. So if I am pulling this block by some amount, what is there? The complete energy is stored in spring, right? In potential energy of the spring. Now if I am releasing that, this energy will be supplied to mass. At equilibrium position, complete energy of the spring will be supplied to the mass, and it will be storing the energy in the form of kinetic energy. After that, it will keep on moving further and it will try to compress the spring further, and then at the time of maximum compression, you know already, the kinetic energy of block becomes zero, and again the complete energy is stored in the form of potential energy in spring. So here also energy keep on oscillating between kinetic energy of block and elastic potential energy of spring. Exactly same thing happen here also, right? So here energy keep on oscillating in the form of electric field and magnetic field. So energy, you can write here, charge also keep oscillating in electric field and magnetic field. And we call this is LC oscillator. So our next point is, let's get the expression for charge and current in the circuit. So initially the capacitor is charged. So let's say let initially capacitor is charged by V0 potential, and then it is removed from the battery and connected here with the inductor. Removed from battery and connected with inductor. Inductor is initially having no current. Okay, so at t equal to 0, here I can write Q0 is equal to CV0. So it is charged to potential V0. So I can write Q0 initially is CV0. So at t is equal to 0, I can write Q is equal to CV naught, I through inductor is 0. This is the condition. Let at time t. Okay, so I will write the charge on this plate. Let's say it left Q. Charge on capacitor is Q, because initially it was Q naught, now it is keep on like supplying some amount of charge, so at some time t it's the charge is Q. Okay, and or either I can write, actually let's say the Q charge has flown, it's like same thing, I just need to take care of the charge and sign on so on actually. So in this situation, and current through inductor is I, and I can write I is equal to what, dq by dt, and here you can write actually Q will be decreasing, so it will be, I can write minus. I hope you understanding, because Q is decreasing, initially it was Q naught. Now I can go for KVL in the circuit, and let apply KVL in circuit. So first at time t, the circuit will looks like this. It is having some charge, this Q, C, L, current I. Clear? So now I can apply KVL in the loop, and so by applying KVL I can write here the equation or the relation between current and the charge is that I'm writing it here. So at this moment of time, let's say it's Q by C potential, it's Q by C minus L di by dt equal to 0. Now the point is, here I have I is equal to minus dq by dt, so I can write here from here di by dt is equal to minus d2q by dt square. Let me substitute it here actually. So this is Q by C minus minus plus d2q by dt square into L equal to 0. This can be further d2q divided by dt square plus q by lc equal to 0. So we got this expression. Now you can see here it's equivalent to a standard equation of SHM. So this is standard equation of SHM. Now if I compare it with the SHM, then I'm getting here actually this is d2x by dt square plus omega square x. So just comparing this equal to 0, I am getting omega is equal to 1 by under root LC. So this is the angular frequency of oscillation of charge. Let me erase this part some. Okay, so we have final relation here is terms of d2q by dt square plus q divided by lc equal to 0. And if I write the general solution of this, then q comes out to be function of t, it's some q naught sine of omega t plus some phi. Phi is the initial phase. So we got charge function of time, because we know the maximum charge, either I can write some q and then I will write at t's maximum charge is q naught, so then it will come ultimately q naught. So now where phi is the initial phase. So we know t is equal to 0, phi is equal to like q is equal to what? Q is equal to q naught, and if I differentiate this, then I got I, and this is equal to what? Minus of dq by dt, and this comes out to be minus q naught omega cos of omega t plus phi. So I have the condition I equal to 0 at t equal to 0. Clear? So first thing is, let me substitute it here. So I'm getting q, it's q naught equal to q naught into sine of omega t is equal to 0, so 0 plus phi. This implies we are getting actually here directly I'm getting it's pi by 2. So that means q here, just wait, let me just check it. So initially at t is equal to 0, if I am writing it this way, then I am getting phi is equal to pi by 2, because initially the charge on the capacitor is maximum. This implies q is coming up, q function of time is equal to q naught into cos of omega t. Clear? And we can check it here also. So if phi I can substitute there also, otherwise I can check it. So in this case t is equal to 0, this should be 0, so it's 0 minus q naught omega cos of, so 0 plus phi, and this comes out to be 0, implies phi is equal to pi by 2. It can be 3 pi by 2 also, we need to check for that. So ultimately, like at this time, is it this is the relation. So finally we got phi, and I am getting I is coming out to be, if I substitute it here, so it's minus q naught omega, and just 1 second, yes, so minus q naught into cos of omega t plus pi by 2, that cos pi by 2 plus theta is minus sine theta, so I is equal to, this is q naught omega sine of omega t. So this is the current as function of time, and this is the charge, and here we can see the energy is also oscillating, and at any moment of time, just like energy is remaining constant in case of SHM, in case of LC oscillator also energy remains exactly same. I can get the same expression from energy conservation method also. So this KVL loop was one way to deal with this situation. We can get all this from energy conservation. So that is second way is from energy conservation. So I can write total energy initially, this is half, I can write q square by 2c. This is the total energy. Energy in inductor means you can write U in L is equal to 0 because there is no current. But at time t, I can write U will be actually half. This you can write q square by 2c plus some Li square. It will be, and total energy will be conserved. If I differentiate it, then I will get du by dt equal to, this is 2q by 2c into dq by dt plus 1 by 2 into 2l I into di by dt equal to 0. 2 gets cancel everywhere. Rearranging, this is I taking it out, and di by dt I am writing d2q by dt. This implies then I am getting this dividing by L, so it's d2q by dt square plus this is q by LC equal to 0. So we are getting again same expression, and here also I can write q is equal to some q naught sine of omega t plus phi, exactly in same manner, and then I will get phi is equal to pi by 2. So we got finally expression q naught into cos of omega t. So phi will depends that initially what is the situation of the system, where exactly energy is stored at t is equal to 0 moment. So this is all about LC oscillation. Here we can plot depending on if this is the variation, then charge, is it q on capacitor as function of time. So this is cos, so cos we know the variation, it will be like this way. is it? And similarly I can plot the uh, variation of current. We can have energy also as function of time, because kinetic energy and potential energy, here they are electric energy and magnetic energy. So electric energy as function of time can be also expressed, because we have already relation of charge and current as function of time. So electric energy, this is given by U, E is equal to Q square divided by 2C. Q is equal to Q naught square, this is cos square omega t divided by 2C, and this is Q naught square divided by 2C into cos square omega t. Similarly, energy in magnetic field, or I can write magnetic energy. So this is energy in magnetic field can be written as half L I square, and that comes out to be half L I is Q naught omega square, this is sine square omega t. So this way we have everything about LC oscillation. So I hope this is clear up to here. Let's see some problem based on it.